Welcome everyone to another OCP Tap call. This is call number 156. I'm very pleased to introduce Roel. Roel has a master's in electrical engineering from the University of 20 and is it correct? 20?
Yeah, Twente.
Yeah,
Correct.
20. And has been working in time synchronization since 2008. Over the course of his career, he has built extensive experience in GNSS timing, standards development, and business development, including 12 years with Arbiter Systems. He has also contributed to several IEEE standards and served as a convener in, oh God, why are these crazy spellings all the time? CGRE working group.
Gray, yes,
Yeah,
correct.
CGRE. There you go.
Yeah.
CGRE group, working group on time. At Fugro, role is helping with bringing Fugro Atomicron to market, supporting access to high accuracy GNSS augmented timing worldwide. Please join me welcoming Roll.
All right. Thanks for the introduction, Ahmad. I'm sorry. I'll remove the Gray next time on the BL.
No, it's okay.
I did reduce it from last year. It was way too long. So yeah, thanks everybody for joining. It's my third time. I thought it's a lot, but I see some other people been here already 10 plus times, I guess. But thanks for having me again. So yeah, I'm the business developer for Fugro Atomicron. And Atomicron is growing. It's a brand name that we carry for anything concerning timing inside Fugro. And I'm here to introduce to you a new service that we developed in the last couple of years. It's a worldwide available geostationary satellite-based time broadcast with sub-100 nanosecond accuracy. So yeah, let me get started. So I'll give you a bit of background why we're doing this. I think it's quite obvious for a lot of people. But in the last 3.5 years, almost 4 years working here, we had a lot of requests from companies. So dive into a bit of the specifications we had set for ourselves and where we are today. What did we meet? What did we maybe not meet? A bit on the technology, of course. How do we achieve what we managed to get off the ground in the last couple of years? And then show you also some results of testing that we did. By the way, feel free to interrupt me if you have questions. I'm totally open to do that. And there should also be plenty of time afterwards to ask questions as well. So background. So yeah, we had a lot of resilient timing requests from end users. We have been selling NMA for GNSS for a couple of years now. People are like, okay, that's nice, but we are actually looking for separate timing sources besides GNSS. There's a lot of troubles that can happen with GNSS, like jamming, of course, and still spoofing, even if you use NMA. So is there anything you can do? So again, if possible, can you do something without GNSS? Because we're afraid it might be disrupted. Um, there was only one scalable alternative, I would say, to GNSS using LEO, which is STL from Iridium today, as you may or may not know. So we were thinking, okay, can we do something different? And we needed to capitalize on the infrastructure that we have had in the last 30 years to actually come up with something that makes sense for us. So we decided to use GEO stationary satellites instead of LEO. If you have been on one of my earlier talks, we use Inmarsat geostationary satellites to distribute correction data for GNSS, also to distribute the navigation message authentication data as well. So it was obvious for us to see if we could use that same channel, that same bandwidth that we already pay for on Inmarsat satellites to also come up with a geo service that can actually serve time without using GNSS. As some of you may or may not know, two-way satellite time and frequency transfer exists for many years. One of the inventors, I'd probably say, from two-way satellite time and frequency transfer is Wolfgang at TimeTech here in Germany. It works really well. NMIs use it to actually compare clocks and timescales, but it's expensive. It has quite a large footprint as well. So we actually set off to see, okay, can we do something with two-way, but then make it one-way, and then still make it scalable? So relatively cheap receiver, small footprint, like maybe what Stellus is using, or maybe even a GNSS receiver kind of receiver in size, in swap, basically. So we came up with some product specifications, and they came through our partner Viavi as well, which we developed this on with. So local GNSS independent on the timing side. So basically, it is really hard. We use internet to actually claim fully independence of GNSS. I don't think anybody can tell me if internet will stay up if there's no GNSS. If it does, then we're actually fully GNSS independent. If it doesn't, then we're locally independent, which is what most people are looking for instances that they're being jammed locally, like in war areas today, for example. So again, we decided to base it on geostationary satellites. One of the key requirements that we set out was to get an absolute time error of less than 100 nanoseconds to a common clock. Let's put it that way. I'll get back on that later. This is to actually meet ITU PRTC levels and actually be able to use this in a telecom application. Now, if you manage to meet sub 100 nanoseconds, you pretty much cover probably 99 point something percent of the applications out there anyway. So that's a big benefit, of course. By the way, when we started out with this project, we were not certain if we were going to make it or not, but I can tell you already we did. So we wanted something that's practically impossible to spoof. It's proprietary, so that makes it easier. Also needs to be very jamming resistant. I'll get back on that as well. We wanted an encrypted signal to even make spoofing even less likely. But again, we already have a proprietary signal as well. So we set out with this specification as well. Key also was over-the-air license activation, so people don't have to get to a clock in the future and actually manually update their license. We also do this with our other products, so it shouldn't be an issue. And of course, the time needed to be UTC traceable to fulfill needs in the finance sector, for example. So, oh yeah, and worldwide availability. So we kind of have that with geo. We do have an exception, of course, in the north and south poles because geostationary satellites are actually hovering above the equator and will not have any coverage there. So how did we start on this? Basically, I got to the technology side. The parts here you might have seen before. This is basically coverage beams that we have already for our GNSS solutions as well. In these areas, we have redundant beams, L-band beams from Inmarsat. So we're like, okay, we can use these beams. We will use these beams, so we have same coverage. Then, so we leverage things that we have. These white dots here are reference stations, GNSS reference stations that we have. They, of course, have internet connections that we already use. So we want to leverage those stations if we need them. We have our Inmarsat geostationary data link. Again, we have the existing ground reference sites and the comms. We have redundant network control centers to do calculations and all that. So let's use all that. Of course, we have the worldwide coverage. But what do we need extra? We needed additional infrastructure. So we needed time references because we're not going to use GNSS for time reference. So we have a time reference at NIST in the US. We have a time reference at PTB in Germany and A*STAR in Singapore. And these are geographically in different locations, of course, because we can only use a time reference in an area where the beam is actually available. I'll get to you, I'll get on that why that's actually needed. And then also we needed to add L-band timing hardware at reference sites. They were only equipped with GNSS receivers, but I'll explain later why we also need that to have L-band equipment for this service. So I'm gonna dive a little bit in how the hell did we manage to pull this off. So here's a very complicated schematic, and I'll take you to it one by one. So basically, we will start at the end user. If you're an end user and you have a receiver for our service, you will receive a binary, let's say a binary message. You receive a message. We know what the message is because we send the message. So the end user receiver will actually time tag that incoming message. Now, the next step is we also have a receiving end at an NMI. So at UTC NIST, for example, we have a data feed from UTC NIST to the receiver. So we can actually time tag that exact same message coming in at NIST, and we know what time it arrives there. So that timing information, we send that in a timing message into our network. It goes to an uplink station. The timing message goes back to the geostationary satellite. And the end user also receives, probably about 30 seconds later, it receives that timing message. So now it had received the original binary message and a follow-up message saying, hey, when you got that message 30 seconds ago, I also received it at NIST, and it was this and this time. And basically, the end user can correct its clock. It's a very simple explanation of how it works. It's, of course, a bit more complicated, but this is the main concept. So the end user updates its time based on the correction message from the UTC-K side. What is key in all of this is actually two things. So it only works in static applications or in applications where you know your position. Now, since it's a GNSS independent service, it's very unlikely if GNSS is out that you know your position if you're on the move. So that's why it will generally not work in a moving application. Not yet today. Maybe in the future we can get there, some smart IMUs or whatever, but they're not too accurate. So you do need to know your location. And then the next thing is, we found that out really quickly. We already knew it actually. These geostationary satellites are not very stationary. They move around hundreds of kilometers in a day. So they hover above the equator, but they make a figure-8 figure up and down hundreds of kilometers. Well, you can imagine what we do is in the end is we measure the distance between the satellite and the receiver as well. It's called L-band ranging. And with L-band ranging, if the distance changes, we cannot know the timing message. In the end, what we do is we calculate back when the message left the satellite. So we need to know the location. So what we did is we set off to actually find the location of the satellite. First, we went to Inmarsat, asked them if they know the exact location of their satellite. They said they do. Turns out they do to a certain degree, but for communication, they don't care too much. So it can still be kilometers off. Well, kilometer off in timing is a big issue. Because basically that gives you a lot of extra nanoseconds and you will never get within 100 nanosecond. Philip asks, is a location motion constraint related to Doppler or because of some other uncertainty? Well, it's mainly because, as I explained, that we need to know the distance between the satellite and the location of the receiver, because we do L-band ranging, so we determine the distance from the satellite to the receiver. Now, having said that, there's still plenty static applications out there. What we decided to do is we use a reference station network to also, from multiple locations, look at the same satellite, and we also determine the orbit of the satellite in real time. And we managed to do it so well that we actually get the distance within meters, basically. Okay. next. So to give you an example, since we need a time directly from a UTC realization to make it traceable to UTC, which is only after the fact, of course, but still, we set up time reference sites. So basically, we have commercially leased rack space. This is an example of PTB in Germany, but it's a similar case at NIST and it's a similar case at A-Star in Singapore. So we have our own modem router, a very fancy shelf. We got that from PTB. I guess it's good isolation. And we got, you see a couple SDRs in the back here, you got a computer. We have directional antennas installed on the roof. In this case, it points at two different satellites because we can track two satellites from this site, and then we can also time tag messages from two satellites and use it. As you can see, it's right next to a nice setup for what's it called? The ESA project Clocks in Space or something. Clock Ensemble in Space. We get 1 PPS and 10 megahertz directly from the UTC realization at PTB. Same thing at NIST, same thing in Singapore. Feed that into the equipment so we can actually time tag incoming messages. Then feed that data out into our network, send it to the end user to adjust its time accordingly. By the way, we have our own contracted internet into the sites as well. We're not even relying on their internet. We have our own internet connection there. As you can see here, two nice antennas with LTE failover. This might still not be enough. Actually, we already know it's not enough. We can still have internet outages. There can actually be problems with the feed as well that we get, and they're best effort. So what we're working on today is to actually get backup sites as well. For the US, Americas region, this will be in Canada. For Europe, we already have access to a site in Norway as well, so we can actually fall back to another reference. In the end, we could always fall back to a GNSS reference as well, but since we want to make it as GNSS independent as possible, we prefer not to do that. Okay, then technology, receiver. Basically, we work together with Viavi on that. You can probably still see Jackson Labs on here somewhere. This is the original Jackson Labs receiver. Jackson Labs was bought by Viavi, of course. They basically have a simple, relatively small board that we just adjusted the software on. So it's integrated in this relatively low-cost COTS receiver. Relatively small size, 35 by 51 millimeters. It outputs a PPS just like a GNSS receiver. It stores license information on the receiver. So anybody buying a receiver like this could get the service in any other product as well. We can do over-the-air activations of licenses straight into the receiver. Fugro has full control of that. So I think that's a pretty good achievement. In the end, I guess we should be able to get this into small GNSS receiver type module as well. But we're starting out with this. Also, there are reference designs available. People can make their own receivers. They don't necessarily have to buy this one from Viavi. That's all possible. But you can buy this one today. It's on the website. Would the precision oscillator improve any of the errors uncertainties in the measurement? Yes, Philip. And actually, what normally would happen is you put this into a GNSS clock and you'll take care of it there. Basically, put as good oscillator as you want in the clock, feed it with this PPS, and filter out all the errors, or most of the errors, depending on the oscillator you choose. So there's also an antenna that goes with this, and that's actually a very important part of the solution. So we can nicely geostationary use a directional antenna. Together with Viavi, we actually designed a special antenna for this. It's a relatively long antenna. It's an 8-coil helical antenna. It is very high jamming resilient, basically because of the directionality. So you really have to be in line of sight of the antenna and the satellite to be able to jam it or very close to it. Of course, if you have an omnidirectional antenna that GNSS is using, for example, you can be anywhere around the antenna and it will influence and your jamming, you will actually take the signal out relatively easy. Our signal isn't very strong, but this antenna has high gain, so that's very useful. We have tested and verified the setup at Pentax and Diesel. So Diesel's now Pentax now called Diesel in the US. So we tested it for a couple of years in a row. We also tested it at Jammatest in Norway. And whenever jamming was going on GNSS, it didn't influence the signal reception. And this is actually could be quite a surprise because the signal is very close to GNSS L1. It's at 1545 megahertz. So if you have a high power signal, you actually have also energy in this part of the spectrum as well. But basically, the directionality of the antenna makes sure it doesn't couple in. Good question, Philip. Yes, if you have higher frequency, yes, it will be much better. It could be much better. We have looked at Ku band already. We actually have tested Ku band with dummy signals. The tracking is really good. You can actually use a dish, which is even better. Our biggest issue using Ku band today is that we don't have any bandwidth on any Ku band satellites. And of course, you can buy it, but because we already have L-band on the Inmarsat satellites, it's something that we can leverage. We don't have to additionally use it. But yeah, that's certainly something that we're considering. So no problem there. How vulnerable are you to direction calibration? I don't know if I understand the question, Jeppe. Sorry. So continue on the antenna, high gain antenna, it's going to integrate at LNA. It does out-of-band filtering of all the GNSS frequencies and also 5G frequencies, some of which are very close to the L-band frequencies. So that's also very interesting because if you install this next to a 5G telecom cell site, which happens probably in the future, we already had it ourselves, then it could influence it. But with this new filter design, the latest filter design that we have in this antenna, it actually filters out those signals very well. It's easy to install. I was a bit worried in the beginning. It's a directional antenna, and the directionality is pretty good. How hard would it be to find the satellite? Now, luckily, Fugro already had apps for directional antennas to find satellites. So basically, there's an Android iPhone app which actually points out the satellites in the sky. I did this I think today. At where I live, I can actually see 3 satellites, although this one's going to be very tricky. It will give you, it can actually give you this direct direction of the satellite just on your phone, but it can also give you azimuth and elevation as well in a table. As you can see, the elevation I would get for IRSat would be very low, so it's probably not reachable. But basically, with this aiding, basically you point the antenna and we have not seen people not getting reception. It's very simple. Okay, then some results. So this is with the COTS receiver, with the antenna you just saw. This is about 1 month of data and the end of last year running into well, the 2nd of January, I guess. Standard deviation of 18 nanoseconds, 150 nanoseconds peak to peak on this signal. So it is within the 100 nanoseconds we set out. This is unfiltered data. If you would now couple this with a nice filtering with another better oscillator, you can actually get this flatter as well. This is with the COTS receiver. We actually even see some better performance using an SDR, but that's of course not something you'd want to use. So we still think there might still be improvement possible in receiver design, but we already meet the spec. And as you can see, over time, the signal is very stable, and it can easily be used. Philip, does Inmarsat sell better orbit information? No, they don't. We asked them, they don't. Public tracking data is also not good enough. We tried that as well, of course. What we did do with Inmarsat is they gave us the information they had. Basically, they make a prediction for the week, or every 5 days or something. I don't remember exactly. And the first couple of days is pretty good prediction, but the longer the time goes by, the prediction gets worse. And we didn't stay within bounds in the last 3 days. We have looked at other commercial solutions because there are a couple out there, but they're very expensive. It was actually cheaper to do our own orbit determination in the end. Okay. Oh, thanks, Jeppe. Now it's clear and I answered it. That's good. Ahmad, do I have the ADEF for it? Good question. Let me see. I might actually have it open here. No, it wasn't this one. No, I think I do, Ahmad, but I have to look for it. And I don't
That
think
was
I can
it,
find
wasn't
it.
it? Like you already had it.
Yeah, but this was from our high accuracy.
I see. All right, no worries.
This was another test we did. Let me check. I probably do. I'm not sure if I have it here. Let me make a note. So we also tested this at the European Commission Joint Research Center in Ispra, Italy. This was an initial commercial service test, I would like to call it. As you can see, we had an outlier, a couple of outliers. The lines are at 100 plus or minus 100 nanoseconds. It was not calibrated. 7 days of data, about 200 nanosecond peak with a couple of outliers. Again, no filtering on this, not calibrated. The equipment is still on site there. We are very uncertain what happened here, why this is such a high peak. It could be because of the antenna installation. We'll have to figure it out. We're going to repeat this test. This was actually supposed to be presented at INPTTI, but we were not happy. Well, actually, Joint Research Center wasn't happy about the reference system they were using. They were also not happy about the installation. They weren't confident everything was good. So we're gonna redo this testing. I'm not sure when yet, but it should be sometime this year. But still, even with these outliers, as you can see, the signal is stable over time, and this is still just the receiver board. If you match this up with a good oscillator, you can get better performance for sure. We actually suspected, because this is quite a big jump all of a sudden, we actually suspected it might be something in the receiver that didn't go well in the loop. We have not seen it all the time though on other receivers, so that's interesting. Again, another measurement run this year. We'll share more data. We also want to have a longer data set than just 1 week, of course, as well. Then another result, jammer test. So as you can see, jammer test is one of the worst locations for us because the antenna is almost pointing at the horizon because it's so much up north. So if you would be in front of the antenna, yes, of course, that is an issue. If you jam in front of the antenna, yes, that's also an issue. But still, we had all the equipment installed there. And I'm taking the Tuesday because Tuesday was a very interesting day. There was jamming and meakening in that day. So the red shaded areas here are actually tests coming through the entire day. So it starts at 9. Last test ended at 6. There was also a test in the evening. I didn't include that one because the antenna wasn't installed. So the red shaded areas are test. The y-axis is in nanoseconds. So the blue, purple, I'm colorblind, probably blue trace here in the middle is the time output. This spike here is somebody walking in front of the antenna. Again, that's one of the issues you have there. The antenna wasn't very high up, but testing hadn't started yet here. The other red up here is the EBNO. So the signal that we get in the receiver on the GEO receiver from Viavi. And then we also side by side had a GNSS DO running just to prove what was going on. So as you can see, some of the tests that GNSS DO actually went through, others didn't. Sometimes the signal went truly fully out during some jamming tests, some weakening tests. So during the day, GNSS wasn't reliable. But during the entire day, during all the tests, we still got PPS outputs. So there was high power jamming from a mountain range. Frequencies were jammed starting at 1545, which is including the frequency band that we do. So it wasn't only GNSS, it was actually inside our frequencies as well, the jamming, and it still didn't go out. Again, there were GNSS weakening tests going on that didn't influence us at all, of course. So we ran a full day without interruptions, basically. Yeah, some conclusions. So it is a tested and a verified solution. It's actually available today. You can buy it today. Oh, here are some of our friends. It's proven jamming resilient. We also at Diesel this year, last month in the New Mexico desert, there are a lot of jamming tests going on that we sailed straight through. Very high power jamming, really close to the antenna. We still go out. Nobody is resilient to that. Any radio signal can be jammed. I'm never going to say we won't. We just want to make it as good as possible. It's easily scalable. It's just like a GNSS receiver. You place it where you want, the signal is available, and you run. Worldwide coverage. Again, we capitalized on our existing infrastructure. We still had to do a bit extra on the orbit determination, but then having internet in some locations and all that, that's very helpful. We do get to the plus and minus, less than plus and minus 100 nanosecond precision. I'd say it covers 99% of the application out there, maybe even more. It's been tested, verified by the Joint Research Center, European Commission Joint Research Center, and we will even do more testing there. Then one last thing I didn't mention yet, second to last. Last month, we actually did US Department of Transportation testing. Viavi, together with Fugro, were selected to carry out testing. They did a couple of weeks testing on this. They did a couple of tests in remote areas. And we're waiting the results. We don't have the preliminary results yet, but we hope to get them within a month or two. And then they will write a final report before the end of the year on alternative PNT sources like this one. In our case, it's only time, no positioning, no navigation, but still very promising. Then the last thing, improvements on precision. We will continue on that throughout the year. Mainly, we can achieve that by even getting better orbits. The orbit's still a big factor into the precision that we get, but we think we can still get better. And yeah, as already asked, KU band is also open. Needs to be a business case to the KU band. With KU band, also we could actually design different signals as well, so we can actually make it much more accurate. It will give a whole lot of extra benefits. But again, we need to get bandwidth on a satellite. We need to preferably a satellite provider that also knows where the satellite is, which generally is not the case. And if that's not the case, then we have to do orbit determination again of those satellites as well. So it's a whole extra work. I mean, that's this one's there now. People can already use it. There's still work for the future. All right, I think that's it. Questions? Philip is already the
Hi,
camera on, so
hi, Roel. Yeah, great presentation. Thanks so much. I'm Phil with Open Lunar Foundation, uh, sponsored time project, right? Lunar timekeeping.
all right.
Um, I have a couple of questions on the link itself. So, like this, in this situation, uh, it seems to me like the satellite is just a part of the transport chain. And since the satellite has global coverage, then you can distribute globally. And
Yes,
you're keeping all of the timing precision yourself and accounting for, you're just basically the sorry, the satellite isn't doing any work
no,
other
no,
than the transmission. Is that right?
correct. The satellite is bent pipe in principle, so we don't even know the clocks on the satellite. Well, we know they're not good, but we don't use them. It's just a bent pipe, and we just use it for data transmission, basically. Yeah.
And since the other side is a receiver, I mean, you mentioned this is one way, but that also means like protocols like PTP, that's out of the question because you need a two-way
Yeah, and that
measurement of that
exists.
link.
That is two-way satellite time and frequency transfer. That exists.
That's and
That's
so
just
you
going back
mentioned,
and forth.
yeah, you mentioned that that was uh, expensive and took a wide footprint. And
Yeah.
I was going to ask if you like, since you already have an L-band reference station, does your reference station do two-way time and frequency transfer?
Well, the reference station, if you mean the timing reference stations that we have at NIST and at PTB and Singapore, they have two-way satellite time and frequency
Those are
transfer
externally
installed.
managed.
Yeah, they're
Yeah,
basically what happens is that these NMIs they buy the equipment, and in this case PTB buys bandwidth on a satellite, and everybody buys in on that bandwidth.
I see. And
That's how.
one last question, might not have the answer, but with orbit determination, um, like knowing where the satellite is a big component. But since these are EM signals, does the relative motion of the satellite and it being geostationary, um, is that fundamentally why this is enabled, or is that an ancillary fact? Like, is that critical to this system design?
It is critical that we know where they are because basically in the end we do L-band ranging,
Right.
and they have to be. I mean, every meter is 3 nanoseconds. So
If you knew where, like, if you, let's say, like, hypothetically, Inmarsat had a better hardware and better knowledge of whatever, but if their satellite was moving relative to you, would that make a difference in the accuracy of the rest of your system or the precision of the rest of your system?
one more time, if the satellite was moving,
Mhm. Um,
relative. I don't think I understand the question. I'm sorry.
um,
It's also because I'm not the design engineer of the system, maybe, but
yeah, yeah, of course. We could follow up as well
yeah, feel free to
later,
drop me an
but
email on that. But I don't think I can answer this, to be
okay,
honest.
thanks.
I have a very smart engineer, by the way, that can certainly answer your question.
Roel, thank you very much for the presentation. Uh, to add to Lyndon's question, what happens not only if the satellite is moving, the user itself is also moving. Both of them are moving.
Yeah, so the end user, I mentioned this should be today you can use it in static applications. You can move it in a moving application, but then you have to update your position all the time. And again, if you want to use uh, if you want to get your position, people normally use GPS, and this is actually something to use when GPS is not available. So it's basically a catch-22 there. So you can use it in a moving application as long as you keep updating your position, because you just keep determining the distance to the satellite all the time, and you need to know your distance to the satellite because you need to know that delay.
Yeah, but the satellite is also moving.
Yeah, but that's why we
Oh,
have the orbit determination. That's why we know what. That's why we determine exactly, well, almost exactly where that satellite is.
And these satellites are geostationary, so
Yeah.
once you identify where it is in the sky relative to the surface, it stays there within
No, it doesn't.
a couple of 100 meters or something.
Hundreds kilometers.
Kilometers, okay.
Yes, that's the biggest issue we had in the beginning. We're like, okay, that satellite, we knew it wasn't stable in that position.
And how quickly does it drift over time, that distance?
I think it's a daily figure eight going up and down, something like this. Yeah. And if you would be in one location where your time reference is, of course, then it's not a big issue because the distance is the same going back and forth. But the further you move away from your time reference, the bigger this issue becomes. Because if your satellite is moving, all of a sudden you have different delays. And this is also why two-way satellite timer frequency solves that by basically sending signal back to the other end. And then it's fairly simple. It's like PTP, for example. And then you do delay calibration in that way. And you can relatively easily do that. But the problem with that is first you need to send back as well. And secondly, we wanted something that broadcasts. So it's much easier. Because else you have to also, whenever a message is coming back, you have to communicate with that as well. It doesn't scale very well.
And a question from the chat from Amir.
Oh,
Did you
yeah,
do
sorry.
spoofing tests or just jamming with the geosatellite?
Well, the thing is, the only way to spoof this is that you need to know what messages we are sending, and then it's encrypted as well. So first you have to break the encryption, and then you have to decode our message, and then try to send that over the air. So yeah, we could spoof it ourselves, technically, but anybody else shouldn't be able to do it. Yeah, the signal itself is not the measurement, indeed. There is, I mean, the key in here is L-band ranging. It's determining your satellite, the distance to your satellite with L-band ranging. We have a pattern on this, and it's actually on the L-band ranging itself, mostly. But then you also need to have a timing message as well to know when a message arrives, where the message actually, or what time it was, basically. Any other questions? If not, I'll make a nice PDF of this, Amat. I'll send it to you. You can post it online. And I will look for the ADAF plot. I might have it somewhere. I also asked my engineer to redraw it. I'm pretty sure I have it somewhere. And then I'll send it to you as well, Amat. Okay?
Awesome. So another question I had, like just to clarify, the Fugro Atomicron satellite, is it a satellite of you guys, or you're
No,
sharing it?
it's an Inmarsat satellite. We
Okay.
just buy bandwidth on the satellite.
Okay. So now this is what I've been always wondering. I think probably I spoke to you and I got a good answer from you, but I just forgot. But it's good to have it like here also documented. What if, let's say, this service get expanded to more satellites, so then you can also geo, and then provides you also the ability to have, aside from, let's say, resilience, you have the ability to do some triangulation.
Yeah, well, when we now that we have this service, people are like, oh, can you also get the position of it?
Exactly.
Well, technically, depending on, What we were thinking of, because on vessels it could be interesting as well,
Exactly.
especially in a defense business. Well, if you're on a vessel, you kind of know you're not at 100 meters high, so the height is kind of nice. And then if you would use two satellites, and I guess you need to know if you're on the north or south part of the Earth, you could technically already know where you are pretty much, in some bounds, of course. So yeah, I just spoke to one of geologists about it last week. He said, "Oh yeah, that'd be interesting." So yeah, if you have more satellites, sure.
So basically, the answer is why not, basically, right?
Yeah, I'm not saying it's easy, and you need more satellites because right now you're only tracking one.
No, where, like, you know what? I've been working on my
Philip
book,
likes
right?
it.
One
Yeah,
of
of
the things
course.
I've been thinking about is, yeah,
Whenever
more
something
satellites.
gets launched, Philip likes it. So, no, why I'm thinking about it is like basically I've been working on my book, right? And
Uh,
I highlighted BPS in my book. So,
yep.
like you reuse basically the whole ATS, and of course the next logical thing, like I think about it is like, okay, what if like the whole, TV infrastructure, and you're like, what about the ones that are in geo? So
Yep.
then you're like, well, of course, it's not going to be a walk in a park. Like you have to also provide some proper timing to these things. I mean, most likely you're not going to be able to retro use, but let's say
Well,
there
that's the
is
thing.
something.
We don't do anything with the timing on a satellite. I mean, we don't
You know,
care
but if
about
you want to
whatever
do
is on the satellite.
positioning, then you need, because then like
I don't think you have
I
to.
really don't know how they work. Like, do they do these geo satellites take the signal from the base station? I really don't have knowledge on the TV world,
They
I'm not
call
a
it
broadcasting person.
they call it a bent pipe.
Okay.
Literally,
So
you
like
send the
they're
information in and it goes
bufferless.
out again.
They're
Yeah,
bufferless. It's not like
Uh,
they take something like if
no,
I was designing them, I
it's
would be like,
in amplified out. That's it.
it's
that's
like
it?
like a
Yeah,
mirror.
yeah. It's very simple.
I
The
mean, I would
D
have designed it differently. I would have had
Yeah,
like an
of course,
uplink with.
of course. If you want to use it for what you want to do, you would do it differently. I
No,
get
no,
that.
even for TV, I would have like, let's say, sent things on uplink much more dense, and then they get decompressed there, and then they get
No,
sent
they
down.
don't.
Why? Because I
They
can
don't.
resend things.
They're very stupid that way. Yes.
I mean,
Yeah.
they are older technology, I'm assuming. That's why.
That too.
Yeah,
Yes.
there's a reason why I was asking about like, oh, what if it was moving quicker? Like if it was in a lower orbit, or what if you don't care how good the satellite is, you just need it to be there for your bent pipe in order to do this method, right?
Yeah.
So
Yes.
I'm thinking of a lot of applications or ways to do this with smaller satellites that have bad clocks. Like, if Inmarsat can do this with like if it's irrelevant how the satellite is, if you could do the orbital position and have that very well known by some other means, then that's what actually is improving your precision.
Yeah.
And yeah.
There's hundreds of ideas out there to make this better. Don't get me wrong.
I
But
would love to hear all of them. I'll follow up.
we're a business, of course, so we also need to make money. And before we invest in that, there need to be customers, So it's yeah.
No, I mean,
And we also wanted to keep
so
this cheap, by the way. And I'm saying cheap because if you want to scale this, you don't want to charge people $100 a month for this. So it's
I mean,
much
this
less than
this
that.
really goes all over the place. Like, for example, now you can have the geo, like, providing the time to the LEO. As the LEOs are passing by, they get synchronized always by a source. Doesn't need to be terrestrial. You basically just from geo to LEO. And then so many things open up. Of course, these are all ideas, and again, basically, Philip and I can, I mean, with you as well, we can take on like open another, let's say, uh, WhatsApp group, and then just go through ideations.
You don't
And
have enough yet, Ahmad? No,
I never
I'm
have
kidding.
I've
enough, you
been
know that.
meaning to actually put some time on your calendar. Rod, I'll add you too. How about that?
That's fine.
Yeah.
I'll add my engineer, by the way, because I won't have the answers for you.
No, but this is really interesting, like uh, there is a huge shift, of course, like for like all video content, I mean streaming content that goes through IP now. And then what do you do with this infrastructure? Should we still continue the space junk or like leave it or reuse it? Or, I mean, there are good examples out there, like for example, how a piece of service was running on Iridium and it
hmm
became its own business, like so a lot of things like this can happen always there, like think out of the box pretty much.
Yeah, I think our biggest challenge on this is we were set on using most of our existing infrastructure and L-band and the very, very small bandwidth that we have because
Mhm.
it's some of the satellites we have 1200 bouts also in data. So it's very small bandwidth, very little data. To get that in there, that was the biggest challenge. And then when we started talking, I mean, we had a request somebody, oh, can you do it on KU band? If you then tell the engineers, can we do it at KU band? They're like, now we can do something really nice. Large bandwidth, high frequency, design our own signal because that's what we didn't design a signal for this. I mean,
That's
we use
awesome.
what's there. So there's a bunch of opportunities out there. Yes.
Mhm. Mhm.
A quick question about the product itself. Do you charge per update, or is this a subscription for like passively?
It's a license per unit per receiver. By the way, we sell it through Viavi. We're not set up to do high volume licensing. So we sell licenses straight through Viavi to end customers. And I think we settled on a minimum of 3 years up to possibly 10 years licenses because again, they're relatively cheap. We don't want to send out invoices for that amount every month.
All right. Wondering, any more questions from the rest of the audience?
All
I
right.
stepped out for a moment, like I didn't see. Did Hisham ask a question? It's impossible Hisham doesn't ask a question.
You did ask
Hisham,
a question.
Hisham,
Oh, Ahmed, how are you?
good, good. How can we not have a question from you, Hisham? Go ahead.
No, I asked a question already.
You
Oh,
did.
The
I
Yeah,
double,
missed
you
it.
did.
I
the
missed it.
double, the double mobility stuff.
Oh, yeah, yeah, yeah.
But Thorowell is saying the client has to update the accuracy of time synchronization all the time.
Yeah.
And the question now, Ahmed, is which application can tolerate this, or which application may break because of this? I don't know.
Roll, didn't you say that your limitation is in you need to have the client or the follower, the time receiver, to be stationary,
Yes.
right?
Known
That's a
Uh,
big,
location
that's a
Well,
is
it
big
doesn't
group.
it doesn't have to be stationary if you know your location, but that's the catch-22. You want
No,
to
no,
use
no.
it when there's no
Just
GNSS.
stationary. The stationary is a huge subgroup.
Yeah,
Like for
stationaries. I
example,
mean, that's a
you
lot of
have all the
majority
all
of
the
the applications.
telecom,
Yes, all
all
the
the
telecom,
telecom is
data
stationary.
center, finance,
Data
power and
center, exactly.
energy.
That
It's all stationary.
a
yeah.
huge
So
thing.
you're
And again,
assuming,
when you
Robert,
have that, sorry, good.
yeah. So Robert, you're assuming that the client doesn't move, correct?
Yes, correct.
So if it moves, the question I'm asking Ahmed and you, if the client moves, then and the satellite LEO move, this double mobility may break some applications, but I don't know
But the
which
satellite is
application.
geo. The satellite
Yeah.
is geo.
So
So
listen,
double mobility doesn't apply.
over the data link, we send the orbit correction for the geo so that actually the receiver knows where the geostationary satellite is. If you can update your own position, because basically you input the position into the receiver, if you can continuously update that position because you know where you are, then you can use it on the move. And I mean, if you'd be,
Not position. I'm talking about time synchronization, time.
yeah, then
So
you
for
get time
LEO,
out of it. You get a
yeah,
PPS out of it.
exactly. So LEO moves.
Oh, but this is geo. This is
it,
geo.
Oh, geo.
Your stuff is a stationary client
Uh-huh.
and geo. Got it.
That's right.
I
Yeah.
missed it.
But
It's a-
again,
it's-
the
it's a-
client
it's
doesn't have to be
broadcasting.
stationary as long as you know where you are.
And if the satellite doesn't have to be, it sounds like the satellite doesn't have to be stationary either, as long as they know where they are, or you
As
know
long
where
as
they
we
Yeah,
are.
know,
you're right.
yes, correct.
Yeah, and it's a lot
Got
easier to estimate where
Got
a geosatellite is.
Which gets a bit harder if you're using LEO.
Exactly. And the case I am thinking about is LEO and mobile clients, double mobility.
Well,
That
in that case, you just call Xona and they'll fix it for you.
Yeah. Rio, he called 911.
Again, I mean, LEO solutions exist, but the issue with LEO, the drawback of LEO is that they use an omnidirectional antenna. And the signal, yes, is much stronger than GNSS, but it's very easily jammed still
Mm,
because of the antenna. And that's also why the biggest advantage in anti-jamming in our solution is the directional antenna. It's an RF thing. It's not anything on the signal or whatever. It's the RF protection that you get from the directional antenna.
got it.
Okay.
Thank you. Thank you very much.
Thank you.
All right. No
All
problem.
right.
Thank you. Right on
All
time.
right.
3 more minutes. Good.
Perfect.
Philip,
All right.
send me an email if you have other questions. No problem. All right.
Oh, thank you.
All right. Thanks a lot.
So we'll see everyone in
Thank
2
you.
weeks by call, hopefully from Alice Otori about optical frequency and timing distribution with femtosecond precision.
We didn't get there yet.
Get there. All right.
Hey, thanks a
Bye,
lot.
Thank you
everyone.
very much.
Goodbye.